Hello everyone, welcome to Civil Galaxy. I am Dr. Pruthviraj B S. Today we shall see a module from the subject structural analysis, that is Kanis method. So this Kanis method is used for analysis of indeterminate structure. If we see few key points, of this Kanis method was first introduced by Gaspers Kani in the year 1947. And the second key point we can note here is this method is based on rotation contribution. And the third point we can note in relation with Kanis method is this method is a displacement method. And the fourth point we can note here is this method is used for analysis of multi-story frames. And the fifth point we can note here is this method is an iterative method. It is based on iteration. This method is an iterative method. So now if we remember our slope deflection equation, what Kani has done here is he has used the same slope deflection equation to modify. So if we remember our slope deflection equation for any span, for a span AB, we know that moment about the span A to B will be equal to MF AB plus 2 EI by L into 2 times of theta A plus theta B minus 3 delta by L. This is the slope deflection equation. So assuming the sinking to be equal to 0, we shall get, or the final equation will be MFAB plus, here this will be 4 EI by L into theta A plus 2 EI by L into theta B. So this 2 EI by L into theta is called as the rotational moment. So this 2a by L into theta, we can write it as rotational moment, that is small m. So we shall see how the equation can be developed by using the same slope deflection equation, how Kani has developed the end moments. To find out the end moments, let us consider a continuous beam of a span A, B, this is A, this is B, subjected to 2 point loads, say W1 and W2. So the beam undergoes a deformation in this way. So here, if I want to find out the slope, this will be theta A, and here this will be theta B. Similarly, due to this loading W1 and W2, there is some development of end moments about A and B. So this we will take it as moment about A to B and moment about B to A. So now if we extend the line of action here, assuming this span to be fixed at both the ends, this is A, this is B. So in the first case, if I assume the span AB to be a fixed beam, be having a fixed end moment about point A, that is fixed moment about point A to B. Similarly, we will be having a fixed moment about point B to A. This is the first case. Similarly, if we consider in the second case where the rotation is allowed only about point A, the rotation is allowed only about point A. So the beam undergoes a deformation in this way. So here we are having theta A. So since the rotation is allowed only about point A, the far end about point B is fixed. So about the near end, as we know, this 2ei by L into theta is the rotational moment. About point A, that is 4ei by L into theta A, which is represented by M. So we can write it as 2 times of M AB. And about the far joint, it will be half. That is moment about A to B. Now similarly, in the third case, assuming the rotation is allowed only about point B, rotation is allowed only about point B. So here this is point A, this is theta B. So since the rotation is allowed near the point B and the far end is fixed here, this will be 2 times of moment B to A, this will be moment B to A. So now if I want to find out the end moments, that is moment about A to B, I have to take the addition of all these 3 cases, which will be equal to the same slope deflection equation can be modified as the same slope deflection equation now can be modified as there is end moment, moment about A to B, which will be equal to fixed moment about AB plus this one 2 times of moment A to B plus moment about B A. Similarly, moment about B to A will be equal to fixed moment about B to A plus this one 2 times of moment about B to A plus M A B. So what Kani has done here is he has taken the same slope deflection equation and he has just modified to arrive the end moments. So as we know in the key points that this Kanis method is based on rotation contribution, let us see or let us try to understand how the rotation contribution works. This rotation contribution. So for understanding this rotation contribution, let us consider a multi-story frame . Let us take this as joint A, this as B, and this as C, this as D, this as E. I am not naming all the joints. For my reference, I am taking only 5 references, that is A, B, C, D and E. Assuming that at joint A, this joint A has undergone a unit rotation, so the beam here or the span here A to B is undergoing a deformation in this way. Similarly, from A to E, as it rotates, it undergoes a deformation in this way. Similarly, A to D, it undergoes a deformation in this way. Similarly, from A to C, it undergoes a deformation in this way. So now, as there is a unit rotation about joint A, there is development of the bending moment or end moments here, which is moment about A to B for this span. Similarly, here it is moment about B to A. Similarly, here is also there is development of end moments, that is moment about A to E. Similarly, there is development of end moment here, that is moment about A to D. Similarly, for the span A to C, there will be moment about A to C. So now, using this equation, if I want to write the end moments about the joint A, I can rewrite this as, by using the same Kanis method equation, it can be rewritten as moment about A to B, here this one, moment about A to B for this span, which will be equal to fixed moment about A to B plus 2 times of moment about A to B plus MBA for span AB. Similarly, for span AC, if I want to write moment about A to C, will be fixed moment about A to C plus 2MAC plus MCA. Similarly, for span AD, that is end moment about point A to D, will be MF AD plus 2 times MAD plus MDA. Similarly, for span AE, which will be equal to fixed moment about AE plus 2 times of moment about AE plus MEA. So now, about this joint A, if you want to have the equilibrium for joint A, equilibrium at joint A, that is summation of all the moments about point A should be equal to 0. That means I have to consider this end moments, moment about A to B plus moment about A to C plus moment about A to D plus moment about A to E should be equal to 0. So now if I consider all this fixed moment about A to B and MAB, that is 2MAB represents the rotation about the near end, and the moment about the small MBA represents rotation about the far end. So for that, see here, so adding all this fixed moment about A to B, we can take it as summation of fixed moment about joint A plus summation plus 2 times of summation of all the moments near for the near end, that is sigma MA, or we will consider this as sigma M dash plus sigma M double dash, which will be equal to 0. The same one we have written here. So M dash, what is M dash? We can call M dash as rotation moment or the rotational moment for near end. For near end. Similarly, m double dash can be written as the rotational moment for far end. For far end. Now, the same can be rewritten here as, that is, 2 times of sigma m dash, which will be equal to minus of sigma m f a plus sigma m double dash. So this can be again rewritten as sigma m dash is equal to minus half into sigma m f a plus sigma m double dash. So this can be written as sigma m dash is equal to minus half into sigma m f a plus sigma m double dash. So we know here, that is m dash, m is nothing but the rotational moment, which is 2 ei by L into theta. This can be rewritten as 2 e I by L is nothing but k, that is the relative stiffness, 2 ek theta. So where this k can be related as, that is I by L, which is nothing but the relative stiffness. Relative stiffness. So now this same m dash, if we write here, which is sigma m dash, can be written as 2 e summation of k into theta. So now by taking m dash by sigma m dash, which will be equal to m dash we have taken here is this one, 2 ek theta, 2 ek theta divided by sigma m dash is 2 e summation of k theta. So this can be written as m dash by sigma m dash is equal to 2 ei and 2 ei gets cancelled, theta gets cancelled, we are remaining with k by sigma k. So this k by sigma k is nothing but the distribution factor from our moment distribution method. So this can be written as the distribution, k by sigma k is nothing but the distribution factor. So if we just rearrange this one, we can write here as m dash is equal to k by sigma k into sigma m dash. So as we know, sigma m dash here is represented by minus half into sigma mfa plus sigma m double dash. So we can rewrite as m dash is equal to k by sigma k into minus half into sigma mfa plus sigma m double dash. So again rewriting this equation, m dash can be written as minus 1 by 2 if you take outside, that is k by sigma k into sigma mfa plus sigma m double dash. So this minus half by k by sigma k can be rewritten as u, which is the rotation factor. So m dash is equal to u into sigma mf a plus sigma m double dash. This u is nothing but minus half into k by sigma k, or we can also call it as minus half into the distribution factor, that is u. So this u is called as the rotation factor. So now we shall see how to analyze the indeterminate structure with the help of Kanis method, that is the step-by-step procedure. The first procedure or the first step we need to follow in Kanis method is to find out or to calculate the fixed end moments. The fixed end moments. Second point, to calculate the relative stiffness, K, and the rotation factor, that is U. And next we have to calculate the rotation contribution, at each joint, So these are some of the procedure which we need to follow while analyzing a indeterminate structure with the help of Kanis method. Similarly, we shall see how to analyze the structure with the help of Kanis method in the coming classes by taking few numericals. Thank you.